Hello, the topic of our presentation is Auditing for Bias, a COMPAS case study. First, a little motivation and callback. In class, we saw that Pro-Publica apparently showed that African Americans were biased against when predicting rates of recidivism. This is the table from class, and we can see that black defendants were more often predicted to be at a higher risk of recidivism than they actually were, whereas white defendants were often predicted to be less risky than they actually were. However, we saw in class that this was not the entire truth. In this project, what we wanted to do was train our own model and do the same sorts of analysis we did in class with the Pro-Publica model and draw conclusions regarding what it means to be fair versus what it means to be accurate, and whether or not there might be trade-off between the two. We trained on 3 different models, and their accuracies are reported in this table here. We performed the standard practice of removing the labels, then separating our data into training and test sets. And we can see that logistic regression has the highest accuracy among the models that we tried. We needed to then pick the best model for our analysis purposes. In order to do that, we created ROC curves for our 3 different models. From class, we know that the area under the curve represents how likely a model is to predict a true class as being actually true. In this figure, you can see that logistic regression has the highest area. So, we went with logistic regression as our model. Once we had our model, the first order of business was to recreate the analysis from class. As you can see in this table on the left, the results do not look so good. In fact, the results are pretty similar to the COMPAS analysis from Pro-Publica. However, when we look at this table on the right, we can see that our model satisfies the classification parity definition of fairness. If you look at the numbers, they are pretty close to 0.7 for all the cases. The next thing on our agenda of analysis was retraining the model with predicted attributes removed, which we did on the same training and test sets. Before detailing the results, let me explain what these histograms are. We took 1,000 samples of 25 predicted labels, each for African Americans and Caucasian defendants. Then we took the means of these 25 points and subtracted the African American means with the Caucasian means. In the end, we had 1,000 data points, which were the difference of means. Then we used those means to make this histogram. As one should expect, if there was no bias, the histogram would be centered around 0, since we are taking the difference between 2 mean rates of predicted rates to recidivate. We will call this metric as our fairness proxy, as we will keep using them in the rest of the slides. But, as we can see, that these histograms are centered around a positive number, which means that African Americans are biased against. The histogram in blue is the model where the protected attributes were present, whereas the histogram in orange is with the protected attributes dropped. As we can see, there is no real difference between the performance between these 2 models. This shows that our model satisfies the calibration definition of fairness, but it might still be biased in the original Pro-Publica sense. The next thing to try was using information filters, which is a library function from skLego. What this function essentially does is takes in the protected attributes as input and translates the input data to a space where the protected attributes are completely removed, including any correlation effects, etc. As we can see in the results, the orange histogram is now centered around 0, meaning that this model trained on data passed through the information filter is more quote-unquote fair, but at what cost? Here, we can see the 3 different accuracy metrics. One without dropping protected attributes is in orange, one with dropped protected attributes is in blue, and finally, information filter is in green. We can see that fairness comes at a cost of accuracy, which might not always be what we want. Now we leave behind our logistic regression model and go with the demographic parity classifier. As you can see from the histogram, the orange one, which is the new model, is slightly better, but the story here is the same. Here you can see 2 graphs which show p% score and accuracy against covariance threshold, which is a hyperparameter controlling the model performance. The lower the p% score, the fairer the model. As we can see from these graphs, there is a negative correlation between fairness and accuracy. We would pick our model at some point where we can satisfy our standards of both fairness and accuracy. Another library classifier we tested was equal opportunity classifier. Again, we see that this model is better, but only barely. The story here, again, is the same as demographic parity classifier. The model fairness comes at cost to accuracy. This concludes our project. We confirm our suspicions from class. Fairness comes at a cost to model accuracy, which might not be what we always want. It depends on our specific cases of use. If you have any questions or concerns, please feel free to reach out to any of us and we'd be more than happy to answer them.